Hello, this is the lecture for section 4.3, logarithmic functions. All right, logarithms are simply the inverse of the exponential function. We study logarithmic functions and exponential functions together because they're very intertwined. Sometimes we use properties of logarithms to solve exponential functions and properties of exponential functions to solve logarithmic equations or logarithmic functions. All right, so what is a logarithm then? Well, it's defined like this. Okay, it has a base, and we would write it log base b, and it has an argument. So x might be the argument. So if we have a logarithm that we write as log base b of x, it's going to be the inverse of b to the x. All right, it's going to be an inverse of the function b to the x, the exponential function. We can write any logarithmic equation as an exponential equation and vice versa. Okay, if we have some equation b to the a equals c, it's equivalent. It's absolutely the same as writing log base b of c equals a. Right? The logarithm here is really just the exponent in the exponential equation. Look, a is the exponent. It's equal to log base b of c. So a logarithmic expression will evaluate to an exponent. All right. Converting from exponential form to logarithmic form is not difficult. Some examples. I'm a very visual person, so I kind of like to think about it as going around the circle. If I have this logarithmic equation and I wanted to write this as an exponential equation, always start with the base and then just kind of go around the circle. So log base 2 of 8 equals 3 is equivalent to 2 in the exponential form. The base is going to stay the same. 2 to the third power equals 8. These are equivalent statements. All right? So we can see that this logarithm, this logarithmic expression, it will evaluate to, right, or simplify to the exponent in its equivalent exponential form. Right? Let's try it one more time. If I was converting log base p of m equals w over to an exponential equation, or writing this statement in its exponential form, start with the base, go around the circle. And I can say that p raised to the w power equals the argument, m. All right. We can write any exponential equation in logarithmic form as well, right? Again, start with the base, go around the circle. Since the base here is 4, in logarithmic form, I would write log base 4. I'm going around the circle, so now the argument, the next thing I need to write is the 64. And then what does that equal? It equals the exponent, 3. Okay. If b to the r equals g, let's hit something down here, there we go. Then, when I go around the circle here, I can say that's equivalent to log base b of g. G is the argument. That'd be equal to r. Right? So the argument of the logarithm is what the exponential expression simplifies to. All right, there are 2 special logarithms. There's the common log and the natural log. Why are they special? They're just the most frequently used logarithmic expressions. All right, the common log is simply log base 10. We typically don't write it, though, when we write a common log. So you might say log base 10 of x, right, equals something, but we typically don't write that. We would write log x. Right? And the common log has a key that you can use to evaluate like say I wanted to evaluate log of 7 or something like that, the key, the calculator key, is the log key. Okay, the log key on your calculator. All right, the natural log is the logarithmic expression with base e, right? And we typically write that as natural log, or ln of x, right? So we could say that the log base e, remember e is just Euler's number, right? it estimates at 2.72, but use the e key on your calculator, gives you the full repeating decimal. Because really it's a ratio is what e actually is. Anyway, log base e of x, we usually write that as ln x, natural log of x, and the key that we use on the calculator to evaluate the natural log is the key that has ln on it. All right, let's see. I think let's pull that up, take a look. Here's a calculator that we can look at. Graphing calculator. Here we see there's the log key and there's the ln key. Okay, let's look at evaluating. Let's see, is that what's next? No, now let's talk about solving logarithmic equations. Right, solving logarithmic equations. The easiest way, most logarithmic equations can be solved this way. Sometimes they need a little manipulating first, but to solve a logarithmic equation, really what you want to do, if you're solving for the argument of the equation, you want to convert that over to exponential form. You want to write that as its equivalent to exponential equation, because those are so much easier to solve, right? So if log base 5 of x equals -1, then we can say that 5 to the negative first power, around the circle, equals x. Well, what is 5 to the negative first power? Well, get rid of that negative exponent, we have to move it down below the dividing line, right, to make it positive. So that becomes 1/5. All right? This just says log x equals 5. Well, remember, log x is common log. When you don't see a base, it's assumed that that base is 10, right? So log x is the same as log base 10 of x. When we convert that over to exponential form, we have 10 to the 5th power equals x. Well, what's 10 to the 5th power? Let's see, that's 10 with 5 zeros on it, right? So there's 10. Now let's add 5 zeros. 1, 2, 3, 4, 5. Okay, 10 to the 5th power is 1,000,000. This last example here is the natural log of x, or ln x. Natural log of x, of course, is log base e of x. Right? If that equals -2, when we rewrite that in its exponential form, we say e to the -2nd power is x. Well, if we wanted to simplify that, that's 1 over e squared, right? We could write it that way as well. All right, so sometimes we want to evaluate a logarithmic expression, or we might call that simplifying logs. Say I have a logarithmic expression, log base 2 of 8, right? Well, recall that I said a logarithmic expression is just the exponent to its equivalent exponential expression, right? So what I want to do to evaluate log base 2 of x is I want to say, what exponent would I put on 2 that would give me 8, right? Well, 2 times 2 is 4, 4 times 2 is 8. So if I put an exponent of 3 on 2, 2 cubed is 8. So I can say that the log base 2 of 8 equals 3. All right. Another thing I can do is I can just say, well, I don't know what it is. Let's just say it's x. I don't know what it is. And let's write that as an exponential equation. Sometimes that's a little bit easier to evaluate a logarithmic expression. All right, so let's write that as an exponential. Let's write its equivalent exponential expression, or now we've made it into an equation. That's going to be 6, and go around to the x, equals 1 over 36. All right, well, how do I solve an exponential equation like this? Well, if I can set one side equal to the other side, just with a variable involved, then it might help, right? It might help. If I could write this right-hand side as 6 to some power, Well, then I would know by the one-to-one property that the powers would have to be equal, right? Let's see, how could I write? Well, 1 over 36, that is 1 over 6 squared, isn't it? Yeah, 36 is 6 squared, so at least I've got an exponent involved. If I want to write 1 over 6 squared as 6 to some exponent, if I bring that 6 squared up above the dividing line, that's going to change the sign on that exponent to negative. So that's going to be 6 to the negative second power, right? So what do I have now? Let's just rewrite it. 6 to the x equals 6. Ooh, my pen just went crazy. Hold on, there it is. Equals 6 to the negative second power, right? Well, by the one-to-one property, x has to equal negative 2, right? So I know that log base 6 of 1 over 36, that's going to evaluate to negative 2, right? Or simplify to negative 2. Look at this next one. There's no base, right? So that means it's log base 10. All right. Well, what exponent would I have to put on 10 to get 0.0001? Ooh, I know that's going to be a negative number. Maybe I want to convert this to exponential form and look at it that way. 10 to the x power, 10 to what power equals 0.0001? Well, 0.0001 is like 1 over, let's see, 1, 2, 3, 4. There's 4 decimal places, right? That's kind of like 1 over 10 to the fourth power, right? 1, 2, 3, 4, 10 to the fifth power. Yeah. So I could then say, whoops, come back. I could rewrite. I could rewrite 0.0001 as 1 over 10 to the what power? Is it fourth or fifth? Let me see. I'm tired in the day here. Let's see. $1,000. There we go. We're moving at 4 decimals, so that's going to have to be 10 to the fourth power up there, right? All right, so now I can see that this is, if I bring it up above the dividing line, right, that becomes 10 to the negative fourth power. And I can see that x equals negative 4. All right, look at this next one, the natural log of e cubed, right? Well, remember, natural log is log base e. So if I rewrite that log base e of e to the third power, or e cubed, then, and I say, well, gee, what exponent do I put on e to get to e cubed? Obviously, that's going to have to be 3. All right? And I could use this technique of converting it to exponential form as well. I could do that. I could say log base e of e to the third power is x, right? Convert it over, then e to the x. My equivalent statement here says e to the x is equal to e to the third power. Clearly, x is 3, and so that's how we'll evaluate by that one-to-one property. All right, now sometimes we have a logarithmic expression that we need to evaluate or simplify quickly, and it's not a base 10 or base e that our calculator can do for us very fast, right? So sometimes we need to use this change of base formula. The change of base formula just says log base b of a is going to be equal to log base c of a over log base c of b. It's a way of converting a funky base in the logarithm to a ratio of common logs or natural logs. Then it's easy to use our calculator to find the value, right? So let's look at some examples. Let's look at some examples of evaluating or simplifying logarithmic expressions. Here we have log of 4. Well, we know that's a common log of 4, right? Well, it's log base 10. So the easiest thing to do with that guy is simply use your calculator. What is the common log of 4? Come on, turn on. If I hit a bunch of keys, eventually it'll come. Aw, come on, I wanted you to work. Let's try turning it off and then on again. There, that worked. All right, let's clear it out. Okay, so the common log of 4, we'll just use the log key, 4, enter, and we can see that the common log of 4 is, whoa, went away, what was it? 0.6020599, and we usually round, we usually like to round logarithms to 4 decimals. So it doesn't have to be, I want you to stay, and it won't. It doesn't have to be, but try this. There, now it stays. It doesn't have to be, but that's sort of the general rule of thumb is 4 decimals. So I would say this is 0.60, refusing to stay, 0.602, and I would round this 0 up because there's a 5, which will cause that to be 1. So 0.6021. All right. If I want to find the natural log of 14, the easiest way to do that is with this calculator as well, right? With the ln key, right? Natural log of 14, when I enter that in my calculator, is 2.639, I'll round that 0 to 1, 2.6391. All right, but what if I want to find log base 5 of 72? Oh, you know, I don't have a calculator key for that, at least not on scientific calculators. I'll show you in a minute. You might have one on your graphing calculators. You do have the ability to do that or can download it. But let me show you how to do this with the change of base formula. With the change of base formula, I can convert log base 5 of 72 to a common log. So log base 5 of 72 is going to be equal to the ratio of the common log, remember log base 10, of 72 divided by the common log of 5. And it's easy to remember. It's easy to remember this change of base formula because, look, the base is down low, the argument is up high. So what's up high stays up high, what's down low stays down low, right? Now this ratio is something that I can plug into the calculator and find out what it is. All right, let's use our common log here. Log of 72 divided by the log of 5. 2.6572. All right. Now I can also use, I can also convert this over to natural log and I would get the same value, right? It doesn't matter because it's a ratio. It doesn't matter if I use common log or natural log. Log base 2 of 1/8. Well, I might be able to do it in my head, right? What exponent do I put on 2 to get to 1/8? I know that that's 2 cubed, so I might not do that one in my calculator. Of course, I could do it in my calculator. Let me show you. There's a, I don't know if this software I have has this function on it. Let's find out. Let's see. Under math, under the math functions, where's my math key? There it is. We have several functions under there. Now, my other calculator has a log base. I'm not sure if it's going to be on this one. You might have one. Let's go down and see what's on here. There it is. It's option A on the math functions, log base, right? And I don't care if you want to use that. Let me choose it. Let me press enter. And look, it's just asking me to put a base, any old base. I'll put 2 in there. And then it's asking for the argument. The argument is 1/8. I'll just type it in as 1 divided by 8. And then my calculator would evaluate that for me. Or I could have done that. Or I could have done that by converting it over to exponential form, right? Like we did before. Here's this last one, log 0.3 of 15, right? I can convert that using the change of base. If you've got the function in your calculator, you can use that. Let's use change of base, and let's do this one with the natural log, because it won't matter. It's going to be the correct value either way. So log base 0.3 of 15 is equivalent to the natural log of 15 divided by, that's an L, the natural log of 0.3. All right, it's the same thing as common log of 15 divided by common log of 0.3. Since it's a ratio, it's going to be the same exact value. Let's see what it is. I'll use the natural log key. ln, natural log of 15, we'll divide that by, oops, I didn't get that 1 in there. Let's go back and put it in. Let's see, we'll say insert 1. There it is. Okay, now divided by the natural log of 0.3. And there we have it. It's a negative 2.2493. All right. Just to prove that common log gives us the same value, let's do it and see. Common log of 15 divided by common log of 0.3. Same exact value, negative 2.249, blah, blah, blah. All right. Okay, so there's another property of logarithms that's extremely valuable when solving exponential functions, and it's the exponent property of logarithms. I love this property. Basically, what it says is if the argument of a logarithm has an exponent, you can bring it down and make it a coefficient to the logarithm, right? So for example, if I have log base 2 of x to the 5th power, I can bring down that exponent and write that as 5 times the log base 2 of x. Very, very, very cool. And by the way, it does not matter if that 5 is in the parentheses or not. It can be outside and it would still work. It may change things if you've got a product or an expression going on in here in the argument. All right, let's look at some examples of using this property to solve exponential equations. All right, if you're somebody that likes a procedure, here's a procedure for you. To solve an exponential equation, you want to isolate the exponential expression on one side of the equation. All right, then take the log of both sides. Okay, then we can use this awesome exponent property of logarithms to bring down that variable. Get it out of the exponent and it will become the coefficient. Or it comes from an exponent, it becomes a product. All right, then we just use whatever algebra is necessary to solve for the variable. All right, let's try a few. All right, we have 3 to the x equals 23. All right, well, what would I do to solve that? I could try converting that over to logarithmic form. That would be fine. Then I could use a change of base formula, or I could use this technique of taking the logarithm of both sides, right? Same thing as adding something to both sides or dividing something to both sides. As long as I do it to both sides, it's fine to take the logarithm of both sides, all right? So what I'm going to do here is I'm going to say the log of 3 to the x is equal to the log, I'm just using common log, of 23, all right? Now I can use this property of logarithms and get that x out of the exponents, right? So then I have x times common log of 3 is equal to the common log of 23. All right, solving for x just involves dividing both sides by log 3. Oops, that's supposed to be a g, not a 3. All right, and I can stick that in my calculator to find out what that is. Log 23, oops, log 23 divided by log 3. And there's the value, 2.8540. Oops. Okay. Note, this isn't that much different from converting this to exponential form and using the change of base formula. Look, if we solved it that way, I'd go around the circle, I would write this as log base 3 of 23 equals x. And then I'd have to evaluate that, right? Well, I can use the change of base formula. If I used common log, I would say that's the common log of 23 divided by the common log of 3. Look, same thing we ended up with here. So there are different techniques that can be used. Sometimes you have to take the log of both sides, though. Sometimes converting isn't going to work for you. Look at this one here. Here we have this exponential 4 to the 2x minus 3 equals 44. I don't think I want to convert that one over to exponential form. I think the easiest way to solve that one is just going to be take the log of both sides. Then I can get that whole expression out of that exponent, right? So when I take the log of both sides, I'll have the log of 4 to the 2x minus 3 equal to the log of 44. All right, then I can bring down that exponent, bring it down. Should be parentheses, I guess. And what I have is 2x minus 3 times the log of 4, I'm not going to use parentheses, it's too many, is equal to log 44. All right, now to solve for x here is going to involve some algebra, isn't it? Yeah, log 4 is just a number. I mean, I could find out what it is with the calculator, but I'd have to round it because the decimals are probably going to go on forever and ever. So I'm just going to keep it as this logarithmic expression, but I'm going to distribute it to both terms in the parentheses. Then what I have is 2x log 4 minus 3 log 4 is equal to log 44. All right, I'm solving for x, so let me get this term without x over to the other side. All right, let's add a 3 log 4 to both sides. All right, so these add out, and I'm left on the left-hand side, I'm left with a 2x times log 4, and that's going to be equal to log 44 plus 3 log 4. All right, since I don't want 2x times log 4, since I just want x, let's divide both sides by 2 times the log 4. All right, so when I do that, look what happens here. My twos are dividing out. I got just x left, and there's the expression that I can evaluate with my calculator to find the value of x. Let's see what that is. All right, so my numerator is log 44. All right, let's put parentheses around the numerator because the calculator is stupid and it won't know to evaluate that full numerator before dividing the denominator unless I put parentheses around it. All right, so we're using common log again. So we're going to say the log 44. Let's close that parenthesis. Plus 3 times the log, and I can do this. My calculator will be okay if I just say 3 log. It'll know that I mean it's 3 times the log of 4. All right, one more parenthesis to close out the numerator. All right, then I'll say divided by, and the denominator is going to need parentheses too, I think. Just to be safe, I'm going to use them. 2 times log 4, I'll just say 2 log 4. Close this. All right, so that's going to evaluate to 2.8649. All right. I love this. I love this property. It just makes solving exponential equations so much better. All right, we have 2 more examples here. I've used up my whole page, so I might have to erase some things. Let's see. Let's do some erasing. So I've got some more page to write on here. Okay, that should be good. Okay, 2 times 1.08 raised to the 4t power equals 7. Notice there's something a little different in the format here with this one than the other ones we were looking at. Look, it has a coefficient, right? Or the exponential expression is being multiplied by something. These didn't have that. Well, what would I do with that when I take the log of both sides? It's in the way, isn't it? I want to divide that 2 away before I take the log of both sides, right? I don't want to have a coefficient in front of my exponential expression. I need to isolate it. I need just an exponential expression on one side, right? And I can do that. When I divide both sides by 2, right, then I've got 1.08. These divide out. 1.08 to the 4t power equals 7/2. Now I think I'll go ahead and take the log of both sides, right? So I'll have the log of 1.08 raised to the 4t power, all right? And that's going to be equal to, I'm using common log. You can use natural log here if you want to as well. You'll still get the same answer, but I'm just using common log. All right, so that's going to be equal to the log of 7/2 or 3.5. I think I'll leave it as a fraction. I don't know. There. All right, now I can get that exponent out of there. I'm going to bring down that 4t. Okay, so then, let's do it over here. I have 4t times the log of 1.08 equal to common log of 7/2. Okay, all I want is t, so let me divide both sides by 4 times the log of 1.08. Okay, these 4s are dividing out. Now I'm left with t. Let's put that in the calculator. And let's see what that value is. Okay, log of 7/2. All right, divided by, I'm going to use parentheses in the denominator just to be safe, 4 log 1.08. I don't want my calculator to think that I want to divide. I want my calculator to think that I want to divide that log 7/2 by 4, right, and then multiply. I don't think it would, but I like to be explicit and make sure the calculator knows exactly what I want. There's my answer, 4.0695. Okay, let's do one more. This one has a base of e. It has this coefficient in front, right? There's something being multiplied by that exponential expression. So let's isolate the exponential expression. Let's divide both sides by 10. All right, then I just have e to the negative 0.03t is equal to 4. All right. Now I can just do what I was doing before. Use common log of both sides. But you know what? This is going to be easier if I use natural log because the base is e. Whenever you have a base e, it's going to be a little easier to do natural log. So I'm going to take the natural log of both sides again, only because that base is e. Leave room to write that. Let's try it again. Okay, natural log of 4. Oh, that's 4/10. Let's try that again. The natural log of 4/10. There we go. All right, now I can bring down that exponent. Let's rewrite it. It's negative 0.03t times the natural log of e is equal to the natural log of 4/10, or 0.4. All right, what is the natural log of e? Think about that for a minute. What exponent do I put on e to get e? It's 1. The natural log of e is 1. That's why I chose to use natural log here instead of log, because it's so much easier. Look, that's just gone because it's just 1, right? So now to solve for t, all I have to do is divide both sides by negative 0.03. All right, so let's see what our value of t is now. Come back, calculator. The natural log of 4/10 or the natural log of 0.4, because that's what the 4/10 is. I'm going to do it that way. Divided by negative 0.03. Is that what that was supposed to be? Boy, I wrote that bad. Let me fix that. Yeah, it's 0.03. All right, what was that value again? Oh, I didn't do it yet. Enter. There it is. It's 30.5430, right? Okay. All right, well, that ends the lecture on section 4.3. Logarithmic, what was that called? Logarithmic functions? Yeah, logarithmic functions.